Hey everyone, welcome back. In this example, I want us to take this factored form of a polynomial and translate it into its expanded form, make some observations along the way, and use those observations to create what we call the rational zero theorem. All right, so if we want to expand our polynomial from its currently factored form, we're going to have to use the distributive property and multiply these quantities in parentheses together. Doesn't really matter which binomials we multiply together first, but I did notice that on the far right here, we have x plus 1 times x minus 1. That gives us that really nice difference of squares pattern that you can double check if you don't believe me. But that should multiply out to just x squared minus 1. All right, so now we've reduced this down to the quantity 2x minus 3 times the quantity x squared minus 1. And now we're going to have to use the distributive property or FOIL to do the rest of our expansion. So the product of our first terms in the FOILing process gives us 2x times x squared for a total of 2x cubed. The product of our outer terms gives us 2x times negative 1 for negative 2x. The product of our inner terms gives us negative 3 times x squared or negative 3x squared. And the product of our last terms gives us negative 3 times positive 1. Sorry, it gives us negative 3 times negative 1, resulting in a positive 3. And so the expanded version of our polynomial, written in that decreasing order, is going to look like 2x cubed minus 3x squared minus 2x plus 3. And so we started with the factored form of our polynomial up here and ended up with our expanded form down here. And from the factored form of our polynomial, we can identify very quickly what the zeros of our polynomial are going to be. Right, so they're going to occur when that factor of 2x minus 3 is equal to 0, when that factor of x plus 1 is equal to 0, or when that factor of x minus 1 is equal to 0. Well, if we solve each of these little equations or factors set equal to 0, for 2x minus 3, our solution occurs when x is equal to 3 halves, right? We had to add that constant 3 to the other side and then divide by that coefficient in front of x to create this 0 at 3 halves. For other zeros at negative 1 and positive 1, there's a little bit less work involved, but technically we still are doing those same steps. And so now what we want to do is make some observations going between our expanded form and our factored form and try to help us use these observations to kind of reverse engineer or find these zeros, right? When we start in this factored form, it's very easy to use those factors to find the zeros. But if we start in this expanded form, it's a bit harder to get the ball rolling and find that first 0, right? Once we have 1 0, we can factor that out and then be left with a smaller polynomial, which usually the smaller the polynomial is, the easier it is to find its zeros. So we mentioned this before when we were talking about graphing our polynomial functions, but if we're looking at a factored form and we want to find like the end behavior of a polynomial function, then we need the leading term to help us find the end behavior, and we can find the leading term pretty quickly just by taking the leading term of each factor and multiplying those together, right? So the product of our leading terms from each of our factors would give us 2x times x or 2x cubed, right? And that's how we get that 2x cubed in our expanded form. And now we have a kind of similar pattern or observation that we can make about the constant term in the expanded form of our polynomial, right? Where is this constant term coming from? It's being created in a way similar to how the leading term was being created. The leading term, again, was created by taking the leading term of each factor and multiplying those together, or taking all the biggest pieces and multiplying those together to create the overall biggest piece. The constant term is created using the same reasoning, but in the opposite direction. What I mean by that is instead of taking the biggest pieces of each factor and multiplying them together, we take the smallest pieces of each factor and multiply those together. Well, for a polynomial, what is the smallest possible piece? Well, it's a constant term, or what we sometimes refer to as a degree 0 polynomial. So if we take the constants from each of our factors, that's a negative 3 times positive 1 times negative 1, and multiply those 3 constant factors together, what do we end up with? well, we end up with positive 3. That's how we create that constant term at the very end of our expanded polynomial. And so this really important observation that we can now make is that these factors that help us find our zeros can potentially be created by just looking at the leading term and the constant term in the expanded version of our polynomial. How do we actually create the leading term? Well, we have to take the leading term of each of those factors and multiply them together. So now the idea is if we wanted to reverse engineer this process, because it's much easier to find zeros in a factored form than an expanded form, is, well, if we can look at the leading term of our polynomial and the constant term of our polynomial in the expanded form, can we use those numbers involved to jump back to that first step working in our factored form? The idea here is, well, how is this 2 in front of the x cubed created in our expanded form? The only way it's possibly could be created, if we think about our polynomial in the factored form, is by multiplying all those leading pieces together. Similarly, the only possible way that plus 3, that constant term in the expanded version of our polynomial, can be created is by multiplying all the constants from the factored form of our polynomial together. And so what that means is the constant term at the end of the expanded version of our polynomial is being created from the constant terms at the end, or the constant terms involved in each of our factors. So that means we can look at this number at the end of the expanded version of our polynomial and factor it, and all those possible factors of positive 3 are the potential values that we can use as constants in these binomials in the factored version of our polynomial. And so that's one of our really useful and helpful observations, that the constant term in the expanded version is created and therefore must contain factors that are constant terms in these binomials that we're multiplying together to create our function in that factored form. And basically the same observation can be applied to the leading term of the expanded version of our polynomial. How is that leading coefficient in front of x cubed in this case created? That 2 comes from the product of the leading coefficients and all of the factors in the factored form of our polynomial. And so our leading term, or that leading coefficient, therefore must contain factors of these leading coefficients from the individual factors of our polynomial in that starting factored form. Now I'm going to try to tie this all together, because the way we can put this together is, well, if we think back to those linear factors, like this most interesting one, 2x minus 3, when we actually use that factor to help us find a zero of the polynomial, notice the constant in our linear factor, that negative 3, ends up in the numerator for the solution for our zero, and the coefficient, that number in front of x, ends up in the denominator. And so the idea here, what we end up calling the rational zero theorem, is exactly this observation, that if we have these zeros for our polynomial, they're these rational numbers, just one integer or one whole number divided by another whole number, then the numerators for our rational zeros or solutions to our polynomials, those numerators have to come from factors of the constant term of our polynomial when our polynomial is expressed in this expanded form, and the denominators of our rational zeros are going to be factors, or come from factors of that leading coefficient part of our leading term of a polynomial. So now let me go ahead and write all that up, summarize it in a nice theorem, and then we'll look at some examples of applying this idea or process. All right, so we've gone ahead and put our observations together and summarized it and created what we call the rational zero theorem. So let me go ahead and read that for us. So if we have a polynomial function called f of x expressed in this expanded form, where we have a sub n times x to the power of n, that is our leading term. A sub n is our leading coefficient. N is the degree of our polynomial. Then we have some lesser terms, a sub n minus 1 to the times x to the power of n minus 1, and so on. We don't actually pay attention to much besides the first piece and the last piece. The last piece is our constant term, referred to as a sub 0. So as long as our polynomial function has integer coefficients, and the number p divided by q is a rational zero of our function f. And one other further little condition about this number p divided by q, this rational number, is that it's simplified as much as possible. All common factors have been canceled out if there are any common factors between p and q. So if we have a rational zero of the form p over q, the idea from our observations is the number in the numerator, that p, has to come from a factor of a naught, that constant term in the expanded version of our polynomial, and q, the number in the denominator of our rational zero, must have come from a factor of a sub n, the leading coefficient of our polynomial when expressed in that expanded form. And so what this theorem allows us to do is notice that if we do have a rational zero for a polynomial function, we should be able to look at these two numbers and all the different combinations of factors of those two numbers to create these p over q quantities. And if we do have any rational zeros, we should be able to find them within that list that we create. All right, so let's go ahead and use our rational zero theorem for this example where we want to list all the possible rational zeros of the polynomial function f of x, which is defined as 3x cubed minus 6x squared plus x minus 2. And so to help me generate this list, we have to find these potential p and q values and then put them together in all the different possible combinations to create these fractions or rational numbers that may be zeros of our polynomial. So according to our rational zero theorem, our p values, or the numbers that could be in the numerator of a rational zero, come from factors of a naught, the constant term in our polynomial. So our constant term is -2. We don't really need the sign so much here. We'll see why. So what are all the different ways that we could factor 2 or -2? Well, +1 and -1 are always going to be factors. And then +2 and -2 are the other factors, right? We could do +1 times -2 to get -2. We could do -1 times +2 to get -2. So those are the 4 factors of -2. And again, the sign doesn't matter, so we could just pay attention to the +2. All right, so we're also going to need all the possible factors of our leading coefficient, a sub n. So a sub n is that number in front of x cubed in this case, so that is a 3. So what are all the different ways we could factor 3? Well, we could do 1 times 3, or -1 times -3. So only 4 options there, plus or minus 1 or plus or minus 3. You're always going to have those kind of plus or minus signs in this process, so make sure not to forget those. All right, and so now we have to construct all the different possible fractions that can be created of this form, p divided by q. So we can take our first p values of plus or minus 1 and divide them by our first q values of plus or minus 1. Well, 1 divided by 1 is 1, so that just simplifies to plus or minus 1. But we can take that first p value of plus or minus 1 and divide it by our second set of options for our q value, plus or minus 3. So in the numerator we have a 1, and in the denominator we have a 3, and we could have any different positive or negative combination here. So plus or minus 1/3 is another potential rational zero for this polynomial function. So we've dealt with all the combinations for p over q, where we have a 1 in the numerator. Now we are going to consider the cases where we have a 2 in the numerator of our fraction p over q. So we could have plus or minus 2 divided by plus or minus 1. That'll simplify to just plus or minus 2. Or we could have plus or minus 2 divided by plus or minus 3. And that'll give us 2/3 or -2/3, depending on the combinations of the signs involved. And these are the 8 possible rational zeros of our polynomial according to our rational zero theorem. But let's go ahead and take this example one step further and now actually figure out which of these 8, if any, are actually rational zeros. You got to remember, the way this theorem works is it does not guarantee that you're going to find every single zero of your polynomial function, or that you're even guaranteed to find one, because it could be possible that all of our zeros are irrational or complex numbers, and we'll talk about those a bit later on. So now how do we determine which of these possible rational zeros actually is, if any, a rational zero? Well, if it's a 0, then if we plug these numbers into our function, we should get the output of 0. So all we have to do is test the outputs of our function at +1, at -1, test f at +1/3 and at -1/3, test f at 2 and -2, and then I'm running out of space over there, so we'd have to also test f at positive 2/3 and negative 2/3. We could also check this using like polynomial long division or synthetic division, but I think that's much more time consuming than busting out your calculator and plugging in some values. All right, so I've gone ahead and plugged in our 8 potential rational zeros for our function into our function, and these are the outputs I encountered. So f of 2/3 and negative 2/3 had outputs of negative 3.1 and negative 6.2 repeating. Remember, we're just looking for the outputs of 0 here, and only one of our inputs actually outputted a 0, and that was when x was equal to 2. So by using our rational zero theorem, we know that x equals 2 is one of the zeros of our polynomial, but that's great because what we know is that every zero of a polynomial corresponds to a factor of that polynomial, and so now we can actually start factoring this polynomial. We're not going to, because we're going to stop this exercise here, but that would be the next step in our process if we say wanted to find all the zeros of this polynomial. We know 1 is going to correspond to this factor of x minus 2. We can now divide our polynomial by x minus 2, be left with a smaller polynomial, in this case a quadratic one, which we could then for sure solve using something like the quadratic formula.